Assalamu alaikum, my dear cadets. I welcome you all. It's a very critical moment to you where the corona pandemic has dispersed everywhere in our country and also all over the world. So be safe and sound and stay your home and don't be anywhere. However you excellent are. I am Mohammad Ashikur Rahman, lecturer in chemistry at Borishal Cadet College. Today, I am going to start my lesson on chapter 2, and the name of this chapter is Organic Chemistry, which is included to your chemistry second paper. The topic which you will be taught today is the concept of isomerism, including stereoisomerism. Here is a learning outcomes for today's class. By the end of this lesson, cadets, you will be able to explain the geometrical isomerism like cis-trans isomerism of alkene and cycloalkane, and you will be able to also explain the properties of cis-trans isomerism. Okay, and finally you have to explain the optical isomerism also. Okay, let's get started about isomerism. You have already known the classification of isomerism. You know that isomerisms are two types, structural and stereoisomerism. The structural isomerism contains chain isomerism, positional, functional, metamerism, tautomerism, ring chain isomerism are already discussed in your previous lecture. But today's lecture is to include the stereoisomerism only, which contains the two types of isomerism like geometric and optical isomerism. Here, simply, geometric isomers differ in their spatial arrangement about a double bond, and optical isomers are differs in the arrangement of atoms in 3D space or three-dimensional space, which create mirror images of each other. Okay, these two types of isomerism will be discussed later elaborately. Okay, first of all, move on to the concept geometrical isomerism. Geometrical isomerism, the definition is the spatial arrangement, the isomers which are differs in their spatial arrangement of each other. First of all, you have to know the conditions for geometrical isomerism. For geometrical isomerism, you have to know that any compound to exhibit bias, you have to previous, first of all, you have to know the types of geometrical isomerism. The geometrical isomerism are two types, cis and trans isomerism. Okay, boys, to exhibit cis trans isomerism, a compound must first have restricted rotation about a carbon-carbon double bond. That means carbon-carbon bond. This occurs in compounds with double bonds and ring compounds. That means, elaborately speaking, that to exhibit cis-trans isomerism or geometrical isomerism, a compound must be restricted to rotation about carbon-carbon bond. This is the first criteria to show geometrical isomerism. And the second condition is that the compound must have two carbons in the restricted rotation environment, that is have two different groups bonded. That means, elaborately speaking, that the second condition is that the double bond containing carbon atoms must contains two different group bonded with the carbon atom. Okay, elaborately can be explained by the same by this figure. Here you see the first structure here, a carbon-carbon double bond is present here, and here the double bond containing carbon, this the right carbon which contain a double bond. Obviously, the left carbon contain also present double bond. So the first condition is that the double bond here free rotation is not possible. Here, if we try to rotate this bond, this carbon bond and this carbon another bond, if we have to rotate around the carbon atom, then it was not possible, because here if we try to rotate this if we try to rotate this structure, obviously the double bond will be broken. So here free rotation is not possible. That means restricted to rotation about carbon-carbon double bond in the previous in the left side. And in the similar way, in the right side structure, obviously it contains a double bond present here. So here this side cannot be rotated around carbon-carbon double bond, because if we try to rotate this structure, then the double bond will be has been broken here. That's why the first condition is uh, fruitful, or obey the first rules in this structure. Now we examine the second condition. The second condition was that the double bond containing carbon must have two different groups. Here you see that here two different side is present here. Here is one group and here is another group, which are different with each other. This can be explained later elaborately for your better understanding. As for example, just observe this structure, chemical compound. This compound is 1,2-dichloroethene. Here you see that there is no rotation about the carbon-carbon double bond, because here if we try to rotate the carbon-carbon double bond, then the double bond will be broken here. That's why here free rotation is not possible in this compound. Now we try the second condition. Okay, here this creates the cis and trans isomer, which are different compounds, because here if we examine the carbon atoms which present here, you see that this is carbon atom, here one carbon atom and here is another carbon atom. Here is carbon atom must contain two different groups. One group is hydrogen group and another one is chlorine group. Here the two different groups is present in each carbon atom. Here this carbon atom, the right carbon atom, present two different groups. One is hydrogen and one is chlorine atom. And here the left carbon atom also contain two different groups or sides like hydrogen and chlorine atom. So the second condition may be maintained in this case. That's why we can say that 1,2-dichloroethane undergoes geometrical isomerism. So we can write the following structure from 1,2-dichloroethane. One here we can prepare the first one, and this is called cis 1,2-dichloroethane, and this is another one structure of the PV of the 1,2-dichloroethane. Here this structure is called trans 1,2-dichloroethane. Here cis and trans comes from the two from an statement like when two similar groups are placed with near with each other with are very closer. That means when two same group are placed are very nearer, not not a far distance, then it's called cis isomer. And when the similar group are placed at opposite each other, that means a far distance located are it in far distance, then it is called trans isomer. Here the first compound, you see that here the two hydrogen group or two chlorine group are placed in the same side about double bond, and here the place is the distance between two chlorine is very closer than the right one. Here you see that the distance between two chlorine atom are more and more than that of the chlorine, the distance between two chlorine atoms in cis isomer. That's why this is called cis and the right one is called trans isomer. Boys, the next one here is a structure says to Cl and says to Cl. This compound name is 1,2-dichloroethane. Here you see that this compound contain only a single carbon bond. That's why free rotation is possible in this case, that if we try it, this side can be rotated with respect to the left one, then the single bond cannot be broken in this case, just rotate but not broken. That's why in this case the first condition will not agree in this case. That's why here free rotation is possible. So here first condition is not undergoes in this case. So we can say that this compound, that means 1,2-dichloroethane, doesn't show geometrical isomerism. Boys, you know, you got it. Here there is free rotation about the carbon-carbon single bond, which doesn't lead to the different group compounds. Now see the next one. This is the another compound CaCl double bond CaCl. Here you see that the compound name is 1,2-dichloroethane. Here this compound already discussed in the previous slide. Here is simply you can say that there is no rotation about carbon-carbon double bond due to presence of a double bond. So this creates the cis and trans isomers, which are different compounds. And the two different compounds are the following below. The left one is cis 1,2-dichloroethane, and the right one is trans 1,2-dichloroethane. Here the left one is cis isomer because of the presence of double bond with two different groups of carbon atom, and here it is cis because here the two similar groups are is located to very similar, is very nearer distances than that of the right one. And here the right structure you will follow that here this compound obviously contain a double bond carbon atom and two different sides with the carbon atom with each carbon atom. And here the two similar groups, that means the chlorine, the two chlorine groups are located a far distance than that of the first one. That's why this compound is considered to be a SAS, a trans isomer. Uh, that's why 1,2-dichloroethene undergoes cis and trans isomer. That means it will follow geometrical isomerism. So the boys, do you know? Can you think that which compound undergoes geometrical isomerism among these four compounds? Okay, just follow the first one. This compound, you see that this compound, the first one, that means the number A compound, this compound contains carbon carbon double bond, and here you see that the carbon atom containing double bond have two different groups. One is hydrogen group and another one is ethyl group, and the left carbon containing double bond have two different group. One is hydrogen group and another is ethyl group. That's why here this the first compound, that means the here the chemical name is 1 2 3 4 5 6, that means hexene. This compound shows geometrical isomerism, so it will give cis and trans isomerism. Now follow the next one, that means the B compound, compound B. Here you see that here all also this compound contain two double bond here, and is carbon, and here you see that is carbon containing double bond have two different groups joined with any carbon, with each carbon. That's why the compound B undergoes geometrical isomerism, and it will give two types of isomerism, like cis and trans isomer. And the next one, if you follow the compound C, and here you see that here double bond is present here around the carbon atom, and each carbon containing double bond have two different groups. One is isopropyl group and one is hydrogen group. So in the left carbon containing double bond have two different sides, and if we follow the right carbon containing double bond, here you see that this carbon also contain two different group. One is the hydrogen group and another group is a butyl group. That's why compound C undergoes geometrical isomerism, so it will give two types of isomerism like cis and trans isomerism. Okay, finally you just follow the compound D. Here compound D contains a triple bond carbon atoms. So boys, you can think here is free rotation is possible. That means here rotation is restricted or not. Here you can tell here free rotation is not possible, but in this case rotation is possible, because if we try to rotate the carbon hydrogen single bond, then I think you think the triple bond cannot be broken, because here the power of carbon hydrogen bond is very less than that of the triple bond. That means the energy needed to break the single carbon hydrogen single bond is very less than that of the energy, the required energy which is required to break the triple bond carbon carbon triple bond. That's why here free rotation is possible, because here triple bond has not been broken here. That's why here the first condition undergoes fails. That's why compound D undergoes doesn't show geometrical isomerism, so it will not give it will not give two types of isomerism like cis and trans isomerism. Boys, you got it? Yes. Okay. The next one, here is a question. Write down the position isomer of C7H14, that means a hexene. You have to prepare the position, all possible position isomer for heptene, and think about which one is responsible for geometrical isomerism. Okay, first of all you have to prepare the all position isomer for heptene. Okay, now first of all we have to prepare the position isomer, and this is the first position isomer for heptene. Here This compound contain a double bond at the first carbon and contain no side chain. That means this compound name is heptwanine. Okay. Now you have to think that heptwanine undergoes cis trans isomerism. The answer will be not, because here this compound obviously present a double bond carbon double bond, but in the first carbon here contain the similar group, two similar group. That means here two hydrogen is present here, but the second carbon obviously contain two different group. One is hydrogen group and one is the raised one. But in the left carbon, that is the first carbon, contain just two similar group. That's why this compound, that means the heptwanine, doesn't show cis trans isomerism. Okay, now the next position isomer. Here the chemical name will be heptwin. Do you think that heptwin is responsible for geometrical isomerism? The answer will be yes, because here the carbon atom containing double bond have two different group. Here the second carbon containing double bond have two different group. One is a methyl group and one is a hydrogen group. And the second carbon, that means the third carbon containing double bond, also contain two different sides. One is hydrogen and another is the rest one. So here rotation may be restricted and two different isomer can be created here, like cis and trans isomer can be created here. Okay, now the next position isomer. Obviously, this isomer, the chemical name will be the heptthreene. Do you think that heptthreene is responsible for geometrical isomerism, boys? Okay, the answer will be obviously right. Yes, heptthreene are responsible for geometric isomer, because here you see that the carbon-carbon double bond contains both two carbons. That means the third carbon and the fourth carbon contains double bond, and each carbon atom containing double bond have two different sides. One is hydrogen and the another is ethyl group. And the fourth carbon, that means the carbon atoms containing double bond in the right side, also contain two sides. One is hydrogen atom and another is the propyl group. That's why the heptthreene is obviously responsible for geometric isomerism. That's why uh, it will give two types of isomerism, like cis and trans isomerism. Boys, you got it? Yes. Okay, boys. Now, uh, okay, boys. Now the home task for you about this structure, about this lecture. The first, the question is contain a creative question, contain a stem which is already taught to you in this lecture. So I think you can easily get solved about these questions. And the following question is a definition of a tautomerism, and then next one is and write, you have to write all possible isomer of pentane, and next you have to explain why meso compound is optically inactive. But this question you have to solve the next one in the next class by observing by understanding the next class. And finally the last one is an analytical question, which is why the compound A undergoes geometrical isomerism but compound D not. And I think this is the most easy type question here. So best of luck, boys. Be safe and sound. No more today. Now I'd like to conclude here. Okay, boys. Thank you and thank you all.